Hi, next we discuss about linear phase direct form FIR structure. It is otherwise known as efficient realization of FIR structure. Here we efficiently realize the FIR filter. We consider an example. The transfer function h of z is given here. When we check this transfer function, it is clear that here the filter coefficients are symmetric. Here the filter coefficients are symmetric. If we take the filter coefficient h of 0 and h of 6, they are symmetry same, and h of 1 and h of 5 are same, and h of 2 and h of 4 are same. So we can say that the filter coefficient satisfy the expression h of n is equal to h of capital N minus 1 minus n, where capital N is the length of the filter. Here the length of the filter is 7, and the order of the filter can be computed by length minus 1. So 7 minus 1, so here 6. So we can say that the filter length is 7 and the filter coefficients are symmetric. This is a category of type 1 filter. The filter coefficients are symmetric with respect to 3. With respect to index value 3, the filter coefficients are symmetric and the length of the filter is odd. So it is a type 1 filter. We discussed about what is a type 1, type 2, type 3 and type 4 in the previous lectures. Okay, so we can rearrange it like h of z is, we know that is y of z by x of z. So we can rearrange y of z like this one. Here we can combine the terms with same coefficient. Okay, the first term here half x of z. Here the last term 1 by 2 into z raised to minus 6 into x of z. We can combine these terms and we can rearrange the filter coefficient like this. Okay, the final transfer function is like this. So the number of terms will be reduced. So the number of multiplication factor will be reduced. So that's why we call it as efficient realization of FIR structure. Here the number of multiplication is reduced. So we can check the realization. How can we do that? Okay, we consider the inverse. Inverse is a transform of this expression. It can be represented as y of n is equal to 1 by 2 x of n, that is the first term, plus 1 by 3, and here 1 unit delay, that is x of n minus 1, and here 2 unit delay, that is x of n minus 2, and filter coefficient is 1, and here 1 by 4 is a raised to minus 3. So here have 3 unit delay. Okay, and next what is 1 by 4 1, that is a raised to minus 4, 4 unit delay x of n minus 4. Then here 1 by 3 x of n minus 5, 5 unit delay, and final is 1 by 2 x of n minus 6, 6 unit delay. This is the inverse is a transform. Okay, then we can realize it like this. Okay, so here we can check x of n is the input and this point is x of n, and this is 1 unit delay, that is x of n minus 1, and this point is x of n minus 2, and this point is x of n minus 3, and this is x of n minus 4, and this point is x of n minus 5, and this point is x of n minus 6. Okay, when we check the expression, it is clear that the filter coefficient of x of n minus 6 and x of n are same. So we can combine those terms, x of n and x of n minus 6, and the filter coefficient is 1 by 2. multiply by common filter coefficient 1 by 2. Then we can combine n minus 2, the term x of n x of n minus 1 and x of n minus 5, because the filter coefficient is 1 by 3 there. So we sum up the term and multiply by 1 by 3. Next term is x of n minus 2 and x of n minus 4. We sum up the term and multiply by the filter coefficient 1. And finally, x of n minus 3 into 1 by 4. Then we sum up all the terms, you will get the structure like this. Here, the number of multiplication is reduced. That's why we call it as efficient realization of FIR structure. We can check one more problem. Here also we get the transfer function h of z, and the filter length is even, n is equal to 6. And we can say that order is equal to n minus 1, capital N minus 1, that is 5. Here also we can check the symmetry of the filter. It is a type 2 filter, type 2 FIR filter. Here also it is, the filter coefficients are symmetric. We can combine the terms with same filter coefficient. Okay, then you will get the expression, and we can plot the figure like this. Okay, you can check the previous figure and this one. Okay, here the filter length is even. Okay, filter length is even. Here we combine, this is x of n and this is x of n minus 1, and here the point is x of n, here x of n minus 2, and here x of n minus 3, here x of n minus 4, and here x of n minus 5. We combine the same terms with the common filter coefficient, and finally we sum up all the terms, you will get the filter structure like this. That's all. Okay, thank you.